Swayam Prabha. Digital India. Educated India.
So, today's discussion is about degradation of materials, and degradation of materials starts from the minute the product has been made. So, even during the course of manufacture, even during the course of storage in the form of an inventory, for instance, there is going to be some degradation taking place, because moisture, the environment in which the parts are stored, everything reacts with the surface of the metallic product. So, the change in the nature of the surface of the metallic product will take place depending upon the kind of environment the part has been or the product has been stored in. So, there are different forms of corrosion. I just mentioned to you about a general attack, a general corrosive attack, meaning there is uniform corrosion taking place just because the workpiece or the product is lying in air. So, because of the moisture present in the air, because of gaseous content in the air, so it is not just oxygen and nitrogen, but there could be many other pollutants which might be present in, especially in the city environments. And therefore, we see very often rusting of steel, for instance. It is much more rapid in cities which are close to the seashore, not as much in the interior of the land, but then close to seashore where moisture is very high. Rusting of steel is very prominent. Blackening of silverware, for instance, due to presence of H2S gas, silver sulfide or silver oxide formation. Tarnishing of brassware is a very common problem which we usually find, again because of interaction or reaction of the surface of the brass with the environmental gases. Now, this is a general corrosion, meaning a general corrosive attack which has a uniform effect on all over the surface. That is, the corrosion or the chemical attack takes place uniformly all over the surface. Now, another form of corrosion is called as galvanic corrosion, where without our intention, when two materials having two different magnitudes of electronegativity come together, well, we might have selected these two materials because of their functional requirements. One material is required to be soft, other one is required to be hard. For example, you want steel and aluminum to be put together, say steel clad with aluminum for some reasons, for reasons of thermal conductivity or whatever. So, for functionality you would have put two things together, but then when it gets exposed to corrosive environment or even air with moisture in it, you would find that the galvanic coupling between two materials will result in corrosion of one with respect to the other. Actually, aluminum is not attacking steel, nor is steel attacking aluminum. Steel is not soluble in aluminum, aluminum is not soluble in steel. So, there is an interface where you might have some intermetallics form, but then that area is not the issue. The issue is the difference in the electronegativities between the two elements and the galvanic coupling resulting in corrosion of one of the elements. Then you have crevice corrosion taking place. You have corrosion in the crevices. So, many times we have two plates put together, or in an assembly we have two components put together, and that generates a crevice at times. So, just like when we fasten two plates together, make a lap joint, then we fasten a bolt. So, we have a washer, we have two plates mating together, and this generates a crevice between the washer and the plate and between two plates themselves. So, this crevice corrosion is something that takes place due to entrainment of the corrosive medium into the crevice or into the gap. So, this is something which is commonly found in submerged assemblies. So, the many things are submerged below the sea level or water level, especially when you have corrosive ions present in the material in the corrosive environment. Then you have pitting, that is formation of very small holes, small pits in the material. So, these pits are formed at various points, and we will see the mechanism of this, but then this is another form of corrosion where the material is eaten away at specific points, and the depth of that pit continues to increase with period of time. Crevice corrosion, on the other hand, very similar to pitting, and so there are similarities between crevice corrosion and pitting, and this crevice corrosion also takes place over a period of time and gets deepened. More and more material gets eaten away as the corrosion proceeds. Then you have what is called as sensitization, and typical problem which we encounter is corrosion of stainless steel when you weld it. So, especially when you take austenitic stainless steel where chromium is added in order to give corrosion protection, when you weld the material, because of the heat, the chromium tends to diffuse and combine with carbon, and then this chromium carbide gets formed at the grain boundaries. So, the result is that there is a depletion of chromium near the grain boundaries. So, there is room for corrosive attack to take place close to the grain boundaries, and then the grain boundaries are rendered brittle. The grain boundaries are rendered brittle because of the chromium carbide settling at the grain boundaries. So, in the vicinity of the grain boundaries, the corrosive attack can be very severe due to depletion of chromium. So, this is intergranular corrosion taking place in case of stainless steel. Similarly, there are many other reasons for intergranular attack. For instance, you have stress corrosion, where corrosion occurs in the presence of stress. So, here the regions of high energy undergo higher corrosion rates. So, there are different reasons why corrosion gets aggravated. So, if you have just one single phase, there is no room for galvanic coupling as such. Still, because of the stress, there is a generation of a region of relatively higher energy, higher strain energy, due to which the corrosion steps in to minimize that energy. So, this is stress corrosion, which is very similar to intergranular corrosion in that the corrosion takes place at the grain boundaries, because these are the regions where the energy is maximum. Then you have what is called as selective leaching, where like in brass, for instance, you have copper and zinc, of which zinc gets selectively leached out, and that is because there is a significant difference between the electronegativities of copper and zinc. We will see the electronegativity series in a minute, but then there is a great difference between the electronegativity of copper and zinc, due to which copper gets the zinc gets leached out. So, the zinc is lost, and that leaves behind a porous mass of copper, with zinc having left the alloy. Erosion corrosion takes place when you have abrasive material which is mixed with a corrosive corrosive medium, and this this erosion corrosion results in removal of corrosion products and exposure of fresh metallic surface for further corrosion. So, in all, there is a cooperation between two mechanisms. One is one does the corrosion, other one promotes corrosion. So, for example, by removing the corrosion products, fresh surface gets exposed and therefore, you have erosion corrosion propagating very rapidly. Similarly, stress corrosion, where corrosion is promoted by the presence of stress. Hydrogen embrittlement is another issue again. Well, there is no reaction as such between hydrogen and the material, but then it results in brittle behavior or sudden cracking or sudden degradation of the material. And how does it happen? Well, hydrogen is present in a diffusible form, meaning atomic form in the material. So, in a dissolved condition, and this atomic hydrogen is able to diffuse very rapidly and it goes up the stress gradient, and wherever the stress is maximum, it will result in a brittle failure. So, this is also called as delayed cracking, meaning that one does not really realize that the hydrogen has entered the system, and when the hydrogen diffuses to a highly loaded region, there is sudden brittle failure. So, if the component were weak, if the design was wrong, it would fail immediately. So, as let us say you take a crane hook, for example, you lift the load, you have the material under stress for a certain period of time. So, cracking does not happen immediately. So, what you believe is that it is strong enough, but then in that time hydrogen diffuses to the point of maximum stress and then results in a brittle failure there. So, brittle failure is very sudden, it propagates very rapidly, and therefore, there is a sudden precipitous failure taking place due to which there can be an accident. So, hydrogen embrittlement is a very dangerous situation. So, we will see all these forms of corrosion as a result of a number of corrosive elements which come into play. So, typically atmosphere, aqueous solutions with dissolved oxygen like sea water, for example, soils, acids, bases, inorganic solvents, as in case of algae, moss, etc., growing on metallic surfaces. So, you have ships which are submerged under water and lot of these growths take place there. Then you have molten salts, liquid metals, and of course, the human body. Especially when you take hospital furniture or hospital related use or even storage of agricultural produce, etc., you can have corrosion taking place because of the organic fluids which are present there. Plus, not only organic fluids, but let us say fungi or many such organisms growing on the as a result of the organic liquids being present. Then soils consisting of different proportion of moisture, oxygen, salt, fertilizers are added. So, alkalinity and various forms of bacteria makes the soil extremely reactive, or it makes extremely aggressive as far as the metallic materials are concerned. Marine environment contains sodium chloride, where chlorine ions are extremely dangerous, and then you have oxygen which is dissolved, minerals, acids, and many other biological factors. If you take environment, you have all kinds of gases which are released from industries which result in acid rain. So, when it rains, you have water mixed with the pollutants and it generates acid. For example, SO2 is evolved, H2S is evolved, several gases are evolved, and when they combine with the rain, they result what reaches the ground is basically acid. So, if you look at these various sources of corrosion on a tonnage basis, atmospheric corrosion due to atmospheric oxygen and moisture accounts for the greatest of losses, because even if the workpiece or even if the product is not in contact with any corrosive element, it is in contact with at least the atmosphere, right. So, the two things, one is oxygen and moisture together form a deadly combination, and that reacts with the metallic surface and results in corrosion. Similarly, aluminums of alloys of aluminum, copper, galvanized steel, which are used for atmospheric applications, are able to resist these atmospheric forces because of the tenacious oxide film that they form on the surface. Aluminum, copper, and then galvanized steel has got zinc on the surface, which is sacrificial coating. So, zinc reacts more with the environment, and therefore, it protects the steel which is inside, which it coats. So, for atmospheric applications, wherever the steel or the substrate is likely to get rusted, you use a zinc coating. So, there are many other corrosive environments, including fresh water, and so depending on the propensity to go into solution, metals have been arranged in a electronegativity series or galvanic series, as it is called. So, you have platinum, which is the most resistant to corrosion because it is most inert. So, you have it is most cathodic in nature, whereas it is increasingly active. So, whatever is increasingly active is anodic. So, even more anodic than this would be potassium, sodium, lithium. So, many such materials which are more anodic, more electropositive in nature would lie below this. So, this is a typical series where giving you the potential that is generated during oxidation, and you have lithium going to lithium plus as it has got a very high oxidation negative oxidation potential, whereas if you go to gold, it has got a relatively high positive potential for oxidation. So, up to these elements you have a negative potential up to hydrogen. So, anything above hydrogen has got a negative potential, meaning it is more anodic as compared to hydrogen, and the ones below are relatively cathodic with respect to they are cathodic with respect to hydrogen. We have seen the mechanism of oxidation, where the oxide scale serves as both the electrolyte as well as the medium through which these ions travel. So, oxygen comes in, so porous medium, and electrons get carried to the surface. So, now if we look at the overall metallic corrosion and whether the corrosion products will be porous or they will be tenacious or what, we have what is called as the pilling Bedworth ratio, which gives us an idea about the density, the relative density of the metal and the oxide. So, rho naught, rho O is the density of oxide, rho m is the density of metal, AO is the atomic weight of the oxide. So, based on the formula. So, it is a formula atomic weight. So, for example, if I take FeO, I have one atom of iron, one atom of oxygen. So, I add the two atomic weights together and I get the atomic weight of FeO. But if it is Fe2O3, then I take two atoms of iron. So, I multiply the atomic weight of iron by 2, atomic weight of oxygen by 3, and then I take the formula atomic weight of oxide as 2 into atomic weight of iron plus 3 into atomic weight of oxygen, giving me the atomic weight of Fe2O3. So, this way I calculate the pilling and Bedworth ratio, and if it is greater than 1, if it is greater than 1, well, ideally it should be 1. Why? Because if it is 1, then the there is no volume significant change in density, there is no significant volume expansion. So, that is why the for a protective film, protective oxide film rather, if the oxide is to protect, the ratio has to be equal to unity. Whereas, if you if the ratio is far more than unity, if it is far higher than unity, then it means that there is compressive stresses which are in the present in the film. Well, normally we do not mind compressive stresses, but then excessive compressive stresses can result in breakage of the film. So, it is no longer rendered protective in nature. So, materials with very high peeling bedworth ratio will result in non-protective films. So, if you look at the peeling bedworth ratios for the protective films, they are very close to 1. So, cerium is 1.16, 1.28, 1.4. So, we were talking about copper. Aluminum has got tenacious oxide film. So, 1.28 is the peeling bedworth ratio. So, we have some ratios. Of course, 1.99 is relatively high, but on the higher side, but still these compressive stresses which are induced are relatively mild in nature. Now, so this ratio is so this is the expression for the peeling bedworth ratio for divalent materials, meaning valency of 2. So, when I say valency of 2 means I am talking about, let us say, FeO, for example. I would not talk about FeO here, whereas here you have other than divalent metals. So, you have the valency other than 2 equal to 2. So, that is why Fe2O3 would I would use this formula, right, as compared to this. So, peeling bedworth ratio would be based on A naught rho m upon A atomic weight of metal into density of the oxide that is formed. So, for divalent metals, because oxygen has got a valency of -2 which is fixed, if the metal oxidizes to a valency of +2, it gives out 2 electrons, and that is taken up by oxygen. Then you have an oxide MO that is formed, whereas for all others, so MO would mean FeO, for instance. For all others where the oxygen and so the A and B, the proportion is not same. So, A and B is not equal to 1, then you have MaOB as the formula. For example, Fe2O3. So, you have 2 Fe plus O3. So, 3 by 2 O2 giving Fe2O3. So, basically that is what we are talking about. So, 2 atoms of iron and 3 atoms of oxygen will give you Fe2O3. So, we are talking about a slightly different formula for. So, here for Fe2O3 you would have A equal to 2. So, it will be A naught rho m upon 2 am rho naught, whereas here it will be equal to 1. So, both are A and B are both equal to 1. Now, oxidation reactions can be of different types. So, not only combining with oxygen, but it could things also could combine with something else, like for example, chloride ions or hydroxyl ions, different kinds of ions, due to which you will get different kinds of compounds. So, that is also oxidation of these elements, and if something is anodic, it is more prone to oxidation. So, if we make an alloy having several elements, then the priority with which one element will go into solution, the priority with which one element will get attacked or one phase will get attacked, depends upon the anodicity or anodic potential of that particular phase or that particular element. So, if the electronegativity of that particular element or the phase is towards the anodic side, then that will go into solution first, whereas the other alloying elements which might have been added would remain still in the metal in an alloyed condition. So, whether a particular alloying element A will go into solution or not will be determined by whether B is present, C is present or D is present, because if we say that as we go from A to D, A, B, C, D, the electronegativity is such that D is more anodic as compared to C, and C is more anodic compared to B, and B is more anodic compared to A, then A will not go into solution until B, C and D have gone into the solution. But if you have just A in the solution, that will promptly go to the I mean, if A is the only alloying element, that will go into solution without any way of protecting it from or preventing it from going to the solution. So, basically the electrochemical series which we have seen helps us in understanding as to what would be the possible sequence of these elements going into the solution when an alloy having several of these elements are present in a given solution. Plus there can be different phases which impart a different degree of anodic nature. So, for example, pearlite would be more anodic as compared to ferrite, and so pearlite would go into solution, pearlite will get attacked first as compared to the ferrite. So, you have other reactions pertaining to hydrogen dissolved in hydrogen ions in an acidic solution, and then so here there is no oxygen present, but then usually in most of the times where in all our corrosive environments we have acid which is present with oxygen in it, and then the situation is quite different, the product is different, and so you have a slightly different reaction. So, we have seen this oxide and oxidation reduction of metals. Now, the formation of cathode and anode does not have to happen when there are two different metals. So, for example, you might have just a single metal, you might have made something out of a single piece of metal like zinc. Now, you see that this region is anodic and the rest of the region is cathodic, so that the zinc goes into solution into the acidic solution. So, this surface is exposed to an acidic solution, and then the entire surface therefore does not get attacked by the solution. What happens is one small area or one small region gets preferentially attacked by the solution, and the rest of the area remains intact. Now, in spite of the fact that zinc piece is an integral piece, how did we get these two different zones? I mean, there has to be some reason why this became anodic and this became cathodic. Who decides what makes this anodic and this cathodic? So, what happens at the anode? The zinc goes into solution, at the electrons get conducted to the surface here, and then you have hydrogen ions, because now you have let us say it is hydrochloric acid, then the Cl minus ions will combine with these, and then H plus ions will come over here, take this electron and become H, and then H and H will come together to form H2 gas. So, you will have H2 bubbles coming out from here, and you have zinc being eaten away as it gets ionized to zinc 2 plus. Now, there can be various reasons why this can form. For instance, we were talking about stress corrosion. So, let us say zinc is in this region is highly stressed. Now, for instance, when you have a sharp change in the cross section, when you make a product which is designed in such a way that there is a sharp change in the cross section, then you will have the region where the stress is very high, the region of stress discontinuity. So, supposing the radius at the change of cross section, the fillet radius is not enough, it is too sharp for instance, then that is enough of a reason why the this region will have a stress concentration due to which it will attract corrosive action, whereas this region with relatively lower stress will not attract so much of a corrosive action. Alternately, you could have no stress at all, but then here the grain size could be a little finer than the grain size here. So, that is also another reason why the corrosive attack can become more severe here, because when the grain size is fine, the grain boundary area, being the area of higher energy, is prone to corrosive attack. So, that behaves anodic with respect to the region where the grain boundary area is smaller, and therefore, again within a single piece of zinc you would find that there is a cathode and anode that is set up on its own. So, it does not need two separate materials all the time for corrosion to take place or for cathode and anode to get set up. You can have just one single piece and with different kinds of properties, some small variation, residual stress for example. The part does not have to even have to get loaded. Even presence of small amount of residual stress can result in that part in that area getting corroded faster as compared to the neighboring area. So, there are umpteen reasons how the residual stress can be generated. Either you quenched it the material too fast, the cooling rates were different, or the heating rates were different. There can be various reasons for residual stresses to get generated, and that is the reason how the reactions take place. So, here the overall reaction is zinc plus 2H plus is Zn2 plus plus H2 gas. So, the fact that H plus ions are available here, zinc gets oxidized to Zn2 plus, and hydrogen 2H plus get reduced to H2 gas at the cathode. So, this is the what happens at the anode, and this happens at the cathode, and both these reactions happen at the same rate. Sometimes you have rusting, meaning metal ion forms an insoluble compound where you have atmospheric degradation or atmospheric rusting. So, you have moisture and oxygen present in the atmosphere, and iron gets oxidized to Fe2 plus, and finally, you get FeOH2, and FeOH2 further gets oxidized to so this is ferrous oxide which get oxidized further in the presence of moisture and oxygen to FeOH3. Now, what is deleterious is the presence of moisture, because if you remove moisture from here, this reaction cannot go forward. So, just the presence of iron and oxygen is not going to make any difference, it is not going to result in rusting, but here presence of moisture causes all the damage. So, we have seen all this earlier, and so we come to the concept of a half cell, which is where you generate a potential or you generate some kind of voltage as a result of this ionization taking place. So, oxidation or reduction reaction that is taking place. And so, when we compare the potential generated with respect to the half cell of hydrogen, then we find that the in some metals they are cathodic and some are anodic. We have already seen this, and we have also seen that when the molar concentration is not just 1 mole. So, here under standard conditions we have taken this to be 1 mole. So, these the corrosive environment is under, or the standard potentials have been studied under a standard condition of 1 molar concentration of these two. So, here the way it operates is that iron goes into iron gets deposited, zinc goes into the into solution, right. The zinc goes into solution, and so the now when zinc goes into solution, it needs some chloride or some ions. So, when Fe gets deposited, these chloride ions diffuse from here through this membrane to the right hand side, and then that zinc goes into solution and forms zinc chloride and gets accommodated there. So, this is how the corrosion occurs, and zinc is on the lower side. So, there is more active as compared to iron, due to which it gets corroded. So, now we come to the cell potential when the molar concentrations are not 1 mole. So, this is the formula for molar concentrations, and if the molar concentrations are the same, then it gets reduced to the same thing. So, these are the equilibrium potentials at 1 molar concentration, and the deviation from that due to molar percentages being different is given by the second term over here. And of course, here the effect of temperature is also considered, which so here you operate at around 25 degrees centigrade, that is room temperature. You see that this is the standard temperature and standard molar concentration at which these potentials have been developed, and so any deviation from that is taken care of by the second term over here. And then at so if we stick to 25 degrees centigrade as the standard temperature, then the effect of pure molar concentration, difference in molar concentrations, would be seen over here or from this formula, and this delta V will get modified depending on these molar concentrations. So, this is for example an illustrative example. So, cadmium getting reduced to cadmium ions getting reduced to cadmium, and nickel getting oxidized to nickel 2 plus. So, this is a nickel cadmium type of cell where you have delta V of 0.073 volts as a result of different molar solutions of nickel and cadmium. So, had it been just 1 mole, you would have just subtracted. So, this would have been the difference. So, it would have been minus 0.403 volts plus 0.250 volts. So, this would have been the value, whereas so it would have been about say minus 0.15 volts or thereabouts, but then because of this it has got modified to minus 0.073 volts. So, because of this differences in molar concentration. So, we have seen that the corrosion rate is dependent upon the time as well as the area that gets corroded. So, larger is the area, then the rate at which the corrosion proceeds or penetrates is smaller. So, now when we go to different forms of corrosion, we would see that the corrosive attack is more severe if the area is small. If you look at CPR, smaller the area, greater is the rate of corrosion. So, if the anodic area is smaller, then corrosion proceeds fast, and this is true of pitting corrosion as well. So, wherever there is a corrosion taking place, there is corrosion occurs in the anodic area, and pitting particularly is very severe because the area of the pit is much smaller than the rest of the plate. So, you have several pits, very small pits made, and corrosion proceeds very rapidly in these pits because of the small anodic area that is available. So, if you have two dissimilar materials to be put together, then one has to consult the galvanic series, and then have anode as large in surface area as possible. So, when we have galvanized steel, when we coat these automotive car bodies with zinc, we galvanize the material, the anodic area is so large that the rate of corrosion is extremely small, and that is the reason we have the protection from corrosion. So, we have an anodic material being put on the material to be protected, and since the area of that anode is much larger, the process of corrosion is smaller. Here is an example of crevice corrosion, how it occurs. We have seen that the presence of hydrogen gets reduced to H plus. Now, here the situation is slightly different. Here you have HCl, so or not HCl, sodium chloride, where you have sodium ions, chlorine ions, H2 and OH, H plus and OH ions. In addition to that, you have this oxygen that is dissolved in the water. So, what happens here is that you have these oxygen ions forming OH minus over here by virtue of the electrons coming in, and Cl minus ions go into the crevice. Okay, the Cl minus ions go into the crevice and start corroding this metal. So, metal gives up its electrons forming M plus. So, these ions as the metal gets eaten away, the more and more of these ions come and react and form these chlorides, and H plus ions react with oxygen in water, dissolved oxygen in water, becoming OH minus ions, right. So, you have lots of OH minus ions because of the presence of oxygen. Had oxygen not been present, had it not been dissolved there, then the H plus ions would also have been present and would have competed with the or would have reduced this reaction or would have reduced the attack. So, by presence of dissolved oxygen, the rate of corrosion gets aggravated or accelerated. So, as you see here, the chlorine ions enter the crevice, and because there is no draining out of these M plus ion, these M plus ion gets concentrated over here, and there is a formation of the reaction product over here. This reaction product is not porous, I mean it is porous, the reaction product is porous, it is not tenacious, it does not protect the surface. So, more and more of these chloride minus ions can go further in and ionize the metal. So, the result of ionization is that the electrons which are given out travel through the metal and they come here and form OH minus ions. So, this is what happens when the over a period of time when plate is immersed in seawater where sodium and chloride is present together with oxygen. So, sodium chloride dissolved in water is bad enough, but then oxygen makes it even worse. So, the mechanism for pitting corrosion is also similar to crevice corrosion, but the pits are very small. So, the area of the crevice, the density might continue to decrease, due to which the corrosive attack might get less intense, but in case of pitting, the anode area is very small and the cathode area is very high, right, and therefore, the pitting proceeds at a very rapid rate. We have seen selective leaching, just I gave you an example of brass, and this is an example of stress corrosion cracking, where the cracking takes place in the region where tensile stresses are high, and these tensile stresses render the region which in a higher stress level. So, the higher energy level. So, supposing you have a large amount of deformation here, large amount of tensile strain, then there is a large number of dislocation density increases. So, this region becomes a region of much higher strain. Now, this region is strain free, there is no strain undergone here. So, as I was saying earlier, the one region of the single piece has undergone some deformation. It is more prone to corrosion because here the energy of cold work, the energy of cold work is stored in the form of dislocations, and it becomes therefore prone to corrosive attack. Plus, you have grain boundaries which are already at relatively high energy levels, and most of the dislocation pileups which would take place at the grain boundary. So, that is why increase in the dislocation density in the grain results in more and more pileups at the grain boundary, leading to the grain boundaries becoming more and more prone to attack from corrosive liquids. So, here for instance you have corrosive attack and corresponding cracking, intergranular cracking in brass. So, then this is erosion corrosion, where the propellers, for instance you have wet steam. So, you have droplets of water in steam hitting the turbine blade at a certain velocity, eroding some material progressively over a period of time. So, these turbine blades, valves, pumps, they are prone to these abrasive material, which as I explained earlier results in corrosion. This is weld decay or sensitization of stainless steel, which I mentioned to you as happening due to chromium getting depleted around the grain boundaries, and then the chromium traveling to the grain boundaries as chromium carbide combining with carbon and then making them brittle. So, hydrogen embrittlement also I have seen, I have told you as something that results in delayed cracking, and what promotes this further is that hydrogen sulfide and arsenic compounds retard the formation of molecular hydrogen. So, they enable hydrogen to be present in an atomic form or diffusible form. So, the result is that presence of H2S etc., they again result in further embrittlement. So, to prevent embrittlement, one can bake the workpiece in before use, so that hydrogen gets removed, and then electroplating or things. So, wherever hydrogen can get entrained in the material, having heat treatment in presence of some moisture, say you have a protective atmosphere and you have some percentage of moisture in it. So, that is enough to cause this embrittlement, because hydrogen at ppm levels is enough to cause this brittle failure. So, that is the reason why heat treatment atmosphere should be maintained devoid of moisture. Sufficient vacuum should be present so that there is no moisture present even in vacuum annealing or vacuum based heat treatment. While we pickle the materials, again hydrogen has a chance to get in. So, pickling has to be done or followed up with treatments which will get rid of the hydrogen, right. So, approaches to corrosion prevention include inhibitors, which react or eliminate chemically active species in the solution. So, inhibitor molecules attach themselves to the corroding surface and interfere with the oxidation or reduction reaction. We have seen that there are reactions at the surface where the anodic material goes into solution, reactions where you have electrons being consumed to reduce the hydrogen ions, for instance. Now, as long as both these reactions, reduction and oxidation reactions, produce or proceed in unison, they proceed at the same rate, corrosion can happen efficiently. But if we add inhibitors, they let us say stop the oxidation reaction, then the corrosion gets stopped. Or if there is a reduction reaction that is stopped, let us say you do not allow the electrons to reach the surface and combine with hydrogen, then what happens is there is the net accumulation of charge which on its own results in slowing down the anodic reaction. So, basically inhibitors are the ones which either react chemically or chemically react to the active species and fix it, meaning that they do not let the aggressive chemicals to react with the substrate or the metallic material, or they can inhibit one of the reactions, either reduction or oxidation, so that the corrosion is, the rate of corrosion is minimized or becomes 0. And then they may also form a thin protective coating on the surface, so that there is no further contact of the corrosive medium with the product. Now, if we have to prevent corrosion by design, while designing the product itself, Well, in service we need to take care of the in service requirements of the product, and therefore we cannot always ensure that the grain size will be fine everywhere, or there will be no cross sectional changes, or there will be the fillet radii will be very generous at all times. So we cannot really ensure that that there will not be residual stress present in the material. So there is always going to be the presence of several such factors which will result in part of the product becoming anodic and part of the product being cathodic, in spite of being made from the same material. But then one should allow for complete drainage and of the solution. So the corrosive solution should be it should be possible to drain it out, and corrosion products to be washed away, so that the corrosion does not proceed any further. So one way to inhibit corrosion is to have frequent maintenance and drain out the corrosive liquids, because there is some limit to which the metal can withstand the corrosion. So we need to keep washing it washing away the corrosive media from time to time. Reduce erosion corrosion, meaning if we reduce fluid turbulence or impingement effects, again by design. So we design the product in such a way that that impingement is not at a very rapid rate, or so for instance you have elbows or changes in direction of a fluid. Naturally the solid portions or solid particles will be impinging onto the surface. Now you can either provide a relatively hard surface in the region where impingement takes place, so that the hard surface is a wear resistant surface, a corrosion resistant surface, and that will take care of the erosion part of it. So it will not get eroded, and it will also not get corroded. So let us say you put a ceramic surface which is resistant to the acid or the chemical nature of the gas or the fluid that is flowing through a pipe, which is having so many bends. So now you have wear or erosion resistant materials like ceramics at least locally, so that you are able to prevent erosion corrosion. Eliminate particles and bubbles from the solution. Now bubbles seem to be harmless, but actually supposing bubbles get pressurized. So when when a bubble gets pressurized and then it explodes due to excessive pressure, it can have a detrimental effect, because the entire energy that is stored in the bubble is given out, and that can have a very damaging effect on the wear and it may cause wear and tear of the surface of the structure. Another way is to remove oxygen. We have seen that oxygen is the culprit. It is the one that creates many issues when dissolved in acids or even fresh water, sea water, and so on. So dissolved oxygen enhances corrosivity of many solutions. So we have seen that in sea water, if oxygen is dissolved, it accelerates the corrosivity, it enhances the severity of the corrosive attack. So we need to therefore degas or remove oxygen from the solution or the liquid that is going to come in contact with the product. One can have protective coatings which are abrasion resistant, inactive to the corrosive environment, adherent, and these coatings can be classified as either cathodic coatings or anodic coatings. So for instance, if you take zinc, then it is anodic with respect to steel, and therefore it would be an anodic coating, but you have a coating that is cathodic in nature, meaning noble. So when you apply cathodic coating, the metal which is being applied as a coating is cathodic with respect to the metal that is being protected. So if you need to really protect the workpiece, then you need to make sure that the workpiece is fully coated. It is entirely coated without a single speck of surface remaining uncoated. That is because if you have coated the workpiece with a cathodic material, then it will resist corrosion as long as there is no gap or there is no scratch or there is no removal of this coating anywhere. But if at some point there is a scratch due to which this cathodic coating has been removed, then the region which is exposed becomes anodic, and that region of gets exposed will have a very small area, very small surface area. So, cathode has a very large surface area, anode has a very small surface area, due to which corrosion will proceed at a very rapid rate. So, cathodic coatings are little dangerous because they work very well as long as the coating is complete undamaged, whereas anodic coatings, even if they are damaged, makes the exposed surface behave cathodic, because the when you have coated steel, let us say with zinc for instance, zinc is anodic. Since it has got a very large surface area, it will get corroded very slowly, but then even if there is a scratch in the zinc coating and then the surface gets exposed, the steel surface gets exposed, still it will tend to behave anodic in nature, and that is why anodic coatings become highly desirable. Avoid stress or residual stress is that is another means. So, it can be avoided partly during design and partly during manufacturing. So, you have rapid temperature changes. So, when you heat treat the material, you quench heat treat, meaning you heat the material to high temperatures, quench it. So, this is what introduces these stresses. Well, it will give you the kind of microstructure you want, but then one has to take care of the stresses generated as well. I mean, one has to take cognizance of these stresses. Uneven contraction, abrupt changes in cross section. Now, if you have multiple phases, then you have each phase having its own electronegativity. So, one phase will be more anodic as compared to the other. So, basically this is an issue. Then there can be different thermal expansions associated with these phases, coefficients of thermal expansion, and due to that these phases can induce residual stresses, particularly when the workpiece is being heated or cooled. So, let us say the workpiece gets heated to a certain temperature above room temperature during work, then these will expand to different extents, inducing residual stresses or inducing stresses in the material, and these stresses will result from differential thermal expansion. The stress distribution in the metal will change over a period of time, and therefore, the tendency to get corroded will also keep on changing. So, this residual stress and stress or stress acting at the cross section. So, if you want to minimize the stress acting at the cross section, you can increase the cross section to sufficiently large size. So, it gives you two advantages. One is it gives you some extra material, so that even if there is corrosion taking place, still the stress is well below the design stress, and the rate of corrosion itself is relatively small, the stress being very small. So, it is important that we avoid the stress and even for the residual stress. So, you anneal the material, for example, you anneal the material and work with that. Avoid corrosive media. So, you have stainless steel which stress corrodes in different environments. So, basically even if you have added elements to protect the workpiece from corrosion, this protection always gets undone under certain conditions, like it gets undone in the presence of chloride ions, or brasses stress corrode in the presence of ammonia. So, we need to therefore avoid this corrosive media for stressed structures but then of course, air, atmosphere with moisture is also a medium which will result in corrosion. So, the corrosion may be little at a little smaller rate, but you cannot always avoid corrosive media. You can reduce the aggressiveness of the corrosive media at best. So, this is another means of protection, namely cathodic protection. We have at the ground level we have seen that you have an anode. Now, this wire has to be coated with some insulator, otherwise what will happen is you have 3 elements, you have copper, you have magnesium and you have the steel pipe, and then let us say magnesium is most anodic, then comes copper and then comes steel, then first magnesium will get eaten away, then copper wire may get eaten away. So, that is why copper wire has to be coated, it is very important. Now, this earth has to be kept watered, it has to be kept in a watered condition, a moist condition for the current to be carried. And then here you have similarly a tank to be protected from corrosion, and again you have the negative polarity of a battery or a power source being connected to the tank, so that it always behaves cathodic. So, you artificially make the workpiece to be protected a cathode. So, it is made into a cathode, particularly installations where you cannot do maintenance on a daily basis. These installations like subsea pipelines or infrastructural developmental pipelines. So, they cannot be dug up and maintained on a daily basis. So, they have to be there for tens of years once they have been laid, and therefore, you need to prevent the corrosion by making them cathodes either in this way or that way, by essentially by cathodic protection. So, here they use an inert anode which is carbon or which is graphite basically, and then the current, again here the intervening soil has to be kept watered, and it should be made in a conducting medium. So, the salts, the various components of the soil will ensure that the soil is conductive in between, but there has to be some moisture that is present there. Now, you have galvanic protection by zinc coating, and so here as you see, I was just telling you that if the galvanic the anodic coating gets broken, then you have again the cathodic region which protects the metal. There is another thing that comes into play is polarization. So, polarization is basically the process where the two reactions, oxidation and reduction reactions, do not necessarily go together. So, go at the same rate. Whenever the reactions do not go at the same rate, then we say that the electrode is polarized. So, here what we see is that you have what is called as a reaction where the two electrodes have been short circuited, these two have been shorted together, and so this gives us the natural rate of polarization, meaning when there is when there is free corrosion or free oxidation taking place. So, oxidation is taking place at one place, and then there is a reduction of hydrogen taking place at another place, another surface like in at the platinum surface, and then you get hydrogen gas. So, you have two types of polarization taking place. One is the activation polarization, where you have here the electrons getting generated. So, here basically you have oxidation taking place, and here electrons getting consumed, right, electrons getting consumed. And so, here electrons are getting consumed. So, here electrons are getting consumed. So, this is reduction taking place. Here you have oxidation taking place, right, and these two lines meet at some point where the two reactions are equal, and so here, so this is the so called over voltage, meaning this is the potential at which the two reactions are balanced. Here the reaction of oxidation is faster, here the reaction of reduction is shown is faster. So, here there is net reduction, there is net oxidation. Here you have a zero so called over voltage or zero potential. We will discuss these concepts of polarization and polarization curves, passivation, etc. in the next class. Thank you very much.